let me redraw the picture I had. And let me show a load which can be connected only to ground. Okay. Now in the biasing picture, gate is connected to VG0 and the drain is connected to VDD. Okay. In general, it has to be connected to some point such that it remains in saturation region. Okay. So let's say we want to connect it to VDD for DC, that is for DC biasing. Okay. But we want it to get disconnected from VDD. If it is connected to VDD even for signal frequencies, then the drain current simply goes into ground, the small signal ground. Okay. So it has to become an open circuit for AC or high frequencies. So whatever you connect here should be a short circuit for DC and open circuit for AC. And what is such an element? The obvious choice is the inductor. Okay, I'll call it L2. And this drain must get connected to the load only for AC. Okay, it should not get connected for DC. So we need an open circuit for DC. So we use the familiar coupling capacitor C2. Okay. Now, how do we evaluate the values of L2 and C2? You can write down the transfer function and evaluate it, but I will take an easier way and do it kind of step by step. Okay. Let me draw the small signal picture of this, and while drawing that, I'll assume that this C1 and C3 are already shorted and so on. Okay. Our interest now is to only find the values of L2 and C2. Between the drain and small signal ground, we have L2, and between that and the load, we have C2, and then we have the load resistance. Okay. Now, first I'll assume that C2 has been chosen correctly so that it's a short circuit. If I do assume that C2 is a short circuit, then how do I evaluate L2? Basically, my output current is this I0 that is flowing through the drain of the transistor, and I want all of it to go into the load. Okay. So all of this I0 must go through the load. It shouldn't go into L2. And L2 and RL are in parallel if C2 is assumed to be a short. So how do you make all of I0 or most of I0 go into RL? The reactance of L2 at the signal frequency must be much higher than the resistance RL. Okay. Almost all of I0 flows into RL if omega L2, where omega is the signal frequency and omega L2 of course is the reactance, it's much more than RL. Okay. So you have a parallel combination of impedances and one impedance is much higher than the other. So all of I0 will go into RL. So that's how you have to choose L2, right? L2 also there is a minimum size constraint. L2 has to be much more than RL by omega. Okay. Now let's see how to evaluate the constraint on C2. Okay. How do you choose C2? The reactance of C2 at the signal frequencies, which is basically 1 over omega C2, must be much smaller than the impedance that appears across it. I really mean the magnitude of the impedance that appears across C2. Okay, this is something familiar to us. We have evaluated earlier in the context of the common source amplifier the transfer function assuming that C2 is a short circuit, and also the transfer function including C2, and we found that if the reactance of C2 is much smaller than the resistance across it, then this condition will be satisfied and you will get the same output voltage and of course the same output current in this case, whether you have C2 or whether you replace it with a short circuit. In this case I am generalizing it to impedance because across C2 you have L2 and a resistance RL. Okay. Now all of this part of the circuit drops out. If I deactivate Vi, if I set Vi to 0, this voltage becomes 0 and that voltage becomes 0. So Gm VGS becomes 0. So this goes away and this is all we have left. Okay. And we can evaluate this condition. It's not difficult. What we want is 1 over omega C2 to be much smaller than the impedance across C2. What is the impedance that appears across C2? RL plus J omega L2. Okay. Once you have chosen L2, you can do this. Now, while discussing the output coupling capacitor in the common source amplifier, I also mentioned another constraint. If this impedance, the reactance of L2 is very large, what can happen is that although this condition is satisfied, the voltage here can be quite different from the voltage there. That is, the voltage at the drain of the MOS transistor is very different from the output voltage, and that's undesirable because the MOS transistor is a nonlinear device and you don't want unnecessarily large voltage swings across it. You know that if you are on a nonlinear characteristic, the larger voltage swing you have, the more of the nonlinearity you exercise. Okay, so you don't want any unnecessary voltage swing at the drain node or any nodes of the circuit. Okay, this will become clearer after we discuss what are known as swing limits, the limits of signals that you can apply to nonlinear devices. But for now you can take it from me that it is desirable to have the drain voltage to be as close to the output voltage as possible. And what was the condition for that? In fact, it was simpler. The condition for that was that C2 must be much greater than 1 over omega RL. That is, the reactance of the capacitance C2 must be much smaller than RL. That is, C2 must appear like a short circuit when compared to RL. Not the total impedance across it, but compared to just RL. Okay, so that's the condition that we are going to use in this case. Alright. So it is possible to AC couple the output current I0 into a load resistance. Okay. If you choose the reactance of L2 to be much more than that of RL and reactance of C2 to be much smaller than that of RL, all of this I0 will go into RL. Okay. The only problem with this is that inductors are usually very bulky and they are not very commonly used. Okay. Now, because inductors are very bulky and are somewhat cumbersome to use, in many cases you don't even use L2, you use a resistance instead. Okay. RD. Now in the complete picture, basically this L2 is replaced by some RD. Okay. Now this again looks very familiar. The output part of it looks exactly like what you had in a common source amplifier. Okay. This part you have RD here, C2 and then RL. So what are the conditions that must be satisfied by C2 for the output voltage to be the same or the output current through RL to be the same, whether C2 is a short circuit or C2 is there? We need the reactance of C2 to be much smaller than RD plus RL, but like I have mentioned many times, for the drain voltage to be nearly the same as the output voltage, we would like the reactance of the capacitor to be much smaller than RL. So we'll assume that we use this. Okay. In case of common source amplifier problems, I've asked you to sometimes use this and sometimes use that, but for now let's say we will use this one. Okay. So if that's the case, C2 becomes a short circuit. Now what is the actual current flowing through the load? This current I0 here is the desired output of the voltage controlled current source. This is equal to Gm by 1 plus GMR1 times Vi. Okay. Now clearly not all of it flows into RL. Okay, assuming that C2 is a short circuit, a part of I0 will flow into RL, and how much is that? This current will be I0 times RD by RD plus RL. Okay, it's just the current divider formula. Now this fraction is going to be less than 1, and you cannot help it. Okay, if you don't want to use a large inductor here, you have to use a resistor. You could try to make the resistor as large as possible, but then you will run into the same problem that you did when you made the common source amplifier. Okay, if RD is very large, then this bias current I0 is going through RD, and to maintain a certain drain voltage which is required for saturation, the supply voltage has to be increased. Okay, so if RD is very large, VDD has to be increased to maintain the transistor in saturation region. Okay. So there is some limit to what RD you can have. So that means that it's only a fraction of this current that goes into RL, and that may be okay because this is still a resistor ratio and may be accurately determined. Okay, so the output current, let me call this IL. IL would be GM by 1 plus GMR1 times RD by RD plus RL times Vi, which is approximately equal to 1 over R1 times RD by RD plus RL. Okay, so this number is still independent of the GM of the transistor, and that can be important. So many times the voltage controlled voltage source is used in this mode. Okay, so you have a resistance RD and this. So this looks exactly like a common source amplifier, except when we had the common source amplifier, we had C3 just going to ground. Now we have an extra resistor R1. Okay, so that completes the voltage controlled current source including biasing. And to AC couple the current, you need an inductor, but you can use a resistor and then take a penalty in the actual fraction of the current that goes to the load. Okay, and it is used like that in many occasions. This is also a very widely used circuit, one of the basic amplifier structures using a single transistor. Okay.